Welcome to this educational video on thermodynamics. Today, we'll explore the fundamental laws of thermodynamics that govern energy transfers and transformations in our universe. These laws are essential for understanding everything from engines and refrigerators to chemical reactions, and even the universe itself. Before diving into the three main laws, let's briefly discuss the Zeroth law of thermodynamics. The Zeroth law states that if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Think of it this way. If object A is at the same temperature as object C, and object B is also at the same temperature as object C, then objects A and B must be at the same temperature. This law provides the foundation for temperature measurement and allows us to use thermometers. Now, let's discuss the first law of thermodynamics. The first law of thermodynamics is essentially the law of conservation of energy. It states that the change in internal energy of a system equals the heat added to the system minus the work done by the system on its surroundings. Mathematically, we write it as delta U equals Q minus W, where delta U represents the change in internal energy, Q is the heat, and W is the work. Let's visualize what this means. Imagine we have a system like a gas in a piston. If we add heat, the internal energy increases. If the system does work, like expanding against the piston, the internal energy decreases. Let's work through a simple example to understand the first law better. Problem: a gas absorbs 500 joules of heat and does 200 joules of work by expanding. What is the change in internal energy? Using the first law equation, delta U equals Q minus W. We substitute the values. Delta U equals 500 joules minus 200 joules. So, the change in internal energy is 300 joules. This means that out of the 500 joules of heat absorbed by the system, 200 joules went into doing work, and 300 joules increased the internal energy of the system. Now, let's move to the second law of thermodynamics. The second law of thermodynamics deals with the natural direction of heat flow and introduces the concept of entropy. There are several equivalent statements of the second law. The Clausius statement says that heat cannot spontaneously flow from a colder body to a hotter body. The Kelvin-Planck statement says that no process is possible whose sole result is the absorption of heat from a reservoir and the complete conversion of that heat into work. At the heart of the second law is the concept of entropy, denoted by S. Entropy is a measure of disorder or randomness in a system. For a reversible process, the change in entropy is given by the reversible heat transfer divided by the absolute temperature. Delta S equals Q reversible divided by T. The most important principle related to entropy is that the total entropy of an isolated system never decreases. It either increases for irreversible processes or stays the same for reversible processes. Let's visualize the second law with some common examples. First, let's consider heat flow. When a hot object is placed in contact with a cold object, heat naturally flows from the hot object to the cold object, never the reverse. Another example is ice melting in a warm environment. The ice cube, which is a highly ordered structure, transforms into liquid water, a less ordered state, increasing the overall entropy. Finally, consider gas diffusion. If we release a gas in one corner of a room, it will naturally spread out to fill the entire space, increasing disorder and entropy. Let's work through an example to calculate entropy changes. Problem: a reversible heat engine absorbs 600 joules of heat at 400 Kelvin and expels 400 joules at 300 Kelvin. What is the change in entropy of the universe? First, we calculate the entropy change for the hot reservoir. The hot reservoir loses 600 joules of heat, so its entropy change is negative 600 divided by 400, which equals negative 1.5 joules per Kelvin. Next, for the cold reservoir, which gains 400 joules of heat, the entropy change is 400 divided by 300, which equals positive 1.33 joules per Kelvin. The total entropy change of the universe is the sum, negative 1.5 plus 1.33, which equals negative 0.17 joules per Kelvin. This small negative value suggests that our process isn't perfectly reversible, as a truly reversible process would have a total entropy change of exactly zero. Finally, let's look at the third law of thermodynamics. The third law states that as the temperature of a system approaches absolute zero, the entropy of a perfect crystal approaches zero. In mathematical terms, as T approaches 0 Kelvin, S approaches 0. One important implication of the third law is that it is impossible to reach absolute zero temperature in a finite number of steps or processes. Let's solve a problem related to the third law. Problem: if a perfect crystal at 0 Kelvin has zero entropy, what is the entropy change if it is heated to 10 Kelvin by absorbing 20 joules of heat reversibly? We'll use the definition of entropy change. Delta S equals Q reversible divided by T. In this case, Q reversible equals 20 joules and T equals 10 Kelvin. So delta S equals 20 joules divided by 10 Kelvin, which equals 2 joules per Kelvin. Since the initial entropy was 0 at 0 Kelvin, the final entropy at 10 Kelvin is 2 joules per Kelvin. Let's summarize the three laws of thermodynamics. The first law is about conservation of energy. Energy cannot be created or destroyed, only transferred or converted. The second law introduces entropy. In isolated systems, processes proceed in a direction that increases total entropy. The third law sets a reference point. As temperature approaches absolute zero, the entropy of a perfect crystal approaches zero. These laws have wide-ranging applications, from designing engines and refrigerators to understanding chemical reactions and even the fate of the universe itself. Thank you for watching this comprehensive guide to the three laws of thermodynamics. These fundamental principles govern energy transformations throughout the universe and provide the foundation for countless applications in science and engineering. Remember, while these laws are simple to state, their implications are profound and far-reaching.